Okay, so we're extremely grateful for Trinity College here in Cambridge for funding this webinar so that it's free to you as participants. Our aim this afternoon is to work on some mathematics together from the latest secondary and post-16 features. Throughout the afternoon, we'll be inviting you at various points to contribute your thoughts using the chat. We look forward to responding to those as best we can. If you haven't already done so, it would help us quite a lot if you could rename yourself. Make sure that the name that you have visible is the one that you prefer, because sometimes we might refer to you if you've posted in the chat. I think at this point then, I'm going to hand over to Claire and Charlie. I'm going to turn my microphone off. I'll be sitting behind and keeping my eye on the chat. So Claire and Charlie, over to you.
Thank you very much, Liz. So the set of resources that we developed for this half-term's feature all had a number theory and modular arithmetic theme. We were given some funding from Heilbronn to develop some new resources, and we also wanted to revamp our public key cryptography article. When we looked at it, we realised there was lots of maths that was involved in public key cryptography, which could be taken back down to sort of age 11. So we created a linked set of resources, starting from the basics of modular arithmetic, working way all the way up to sixth form and public key cryptography. So the first thing I'm going to do is I'm going to do some screen sharing, and I'm going to navigate to the resources. So hopefully you can see the NRICH homepage now, and Charlie will shout if you can't. To navigate to the feature, if you go to secondary teachers, then you should find a button which says latest feature. I tend to just click on the pictures now because it's easier. And here we've got the sets of resources that we put together. So dozens we talked about last time. We're not going to talk about that now. We're going to start by talking about clock arithmetic. So Charlie, did you want to say something about clock arithmetic first?
Okay, like Claire says, we're not going to talk about dozens, but if any of you missed last webinar, you can find a recording of that webinar in the teacher's notes to dozens. So it's been saved and it's been uploaded. It remains a live problem, partly because it's also live for primary students at present. Okay, so clock arithmetic, we thought, as Claire said, was a good starting point for modular arithmetic and for the ideas that are going to be built on as we progress towards the public key cryptography article and interactivity that we're going to show you at the end. So it starts there with an image of a clock, using a clock as the model for what we're going to be talking about and how we'd like students to be thinking about modular arithmetic. So 12-hour clock, and then the first task that we have asks some questions like this. Now, if Claire just scrolls down quickly, you'll see that there are 6 different tasks here, and for each, there are also some solutions. So this is slightly unusual for an NRICH problem, but we thought that we wanted students to get started and be able to just check, and they're very short questions, and it's just to check understanding, give them reassurance before they get to both task number 6, which is a bit more challenging, and the follow-on problems. So this is sort of short and sweet and an introduction. So in task 1, could you click on task 1? Let's think about, I don't know, the 4th bullet point as an example, a representative of what's here. What time is 20 hours after 5 o'clock? And I'm imagining that some students might say, oh, well, if I need to think about 20 hours after 5 o'clock, I might be thinking, well, it's 5 o'clock now, so in 12 hours time, it's going to be 5 o'clock again. And then I've still got to add another 8 hours. So adding 20 hours is the same, it's going to give me the same answer as adding 8 hours. And 5 plus 8 is 13, which is, oh, that's 12 plus another 1. So it's going to be 1 o'clock. Now, Claire, you had a different way of doing this problem. Can you remind me what your way was?
Yes. So I went for 5, which is our starting point. Add on 20 gives me 25. And then I know that 25 is the same as 12 plus 12 plus 1. So I know it's 1 o'clock.
Okay.
Which is a slightly more abstract way of thinking about it, I think.
And then once Claire had come up with that, I thought, I've got another way of doing this as well. Adding 20 hours is the same as adding 24 hours and then subtracting 4 hours. So if I add 24 hours to 5 o'clock, it's going to be 5 o'clock again. And then I've got to subtract 4 hours because I've added 4 hours too many. And that's going to be the same as 5 take away 4. And that's another way of getting 1 o'clock. So we'd like students to be able to introduce to modular arithmetic, thinking about clocks in this sort of quite flexible way, in which possibly many of us do time calculations in real life. So let's just very quickly give you show you what we have for tasks 2, 3, 4, and 5. In task 2, I think we then go into mod 7 because we want students perhaps to think about days of the week, which is what we're going to be asking them later on. So there's some simple sort of arithmetic in using modular arithmetic sort of terminology, thinking about equivalence, what's equivalent to 2 plus 3 in mod 7, for example. In task 3, it's again a little bit, it still sticks to mod 7, and we're thinking about subtraction in mod 7. I think task 4 again has subtraction and thinking about adding and subtracting. So you can be thinking of adding as going clockwise around the clock and subtracting going anti-clockwise. So subtracting 1 is the same as adding 6, that kind of idea. So that's what task 4 is. And you can see for every task, we've published some solutions so students can just check that they're on the right track. And finally, task 5 also gets students thinking about slightly larger numbers in size, in the kind of way that Claire and I were talking about. So 50 mod 7, well, I know that 49 mod 7 is 0 because I know 7 sevens are 49, so 50 is 1 more than that. So that idea of going around the clock. And hopefully all that will be good preparation for task 6. And given that we've been working on the tasks and the solutions for 1 to 5, we thought we'd get you working on a couple of these questions. So could you have a look at the first bullet pointed question in task 6? If today's a Monday, what day will it be in 31 days' time? And here's a chance for you to post something in the chat and perhaps tell us how you got at the answer. And in the way that Claire and I suggested, there's often more than one way of doing this. You may find, yes, you've got more than one way of answering that question. So I'll shut up for a minute or two, give you a chance to think about that one, and then give you a chance to write something in the chat.
We have a couple of different answers, which is nice.
Yes, there's slight disagreement about whether it's going to be a Wednesday or a Thursday. If today is Monday, I think in 7 days' time, it'll be Monday again, won't it?
Yeah.
So in 1 day's time, it'll be Tuesday. In 2 days' time, it'll be Wednesday, Thursday, Friday, Saturday, Sunday, Monday. So in 7 days' time, it'll be Monday again. And in 14 days' time, it'll be Monday again. In 21 days' time, in 28 days' time, it'll be Monday again.
Yeah, I think I can see where the misread is coming. So if you start on, as Charlie said, if you start on Monday and add 7 days, you get to Monday. If you add 7 more days, you get to Monday. If you add 7 more days, you get to Monday, and so on. That leaves us with 3 more days to add on, which gives us Thursday. If we think that Monday is the first of the month, so it's the first of something or other, then in 31 days' time, we would end up at the 32nd of the month. So if we add on 31, we go from 1 to 32. So what we're not saying is, we're not saying that if today is Monday the 1st, what day will it be on the 31st? We're saying, what day will it be in 31 days' time? Now, obviously, the 32nd doesn't exist, but that's kind of what we're thinking of. So if we said that Monday is a 1, Tuesday is a 2, Wednesday is a 3, and so on, then Monday will also be an 8, Tuesday will be a 9, and so on. If we take 32 and start subtracting 7s, why am I taking 32? Because it's, if we're adding on to 1, 32, we end up with remainder 4, which means that we're going to end up with a Thursday. So yes, I mean, days time, I think you might want to possibly start with a smaller example, like in 2 days' time, in 3 days' time. What this reminds me a bit of is my youngest child once claimed that she was only 1 year younger than her sister, because she was 5 and her sister was 7, and there was only a 6 in between them. So it's sort of counting the gaps rather than the number of numbers in between. So that's quite a nice question. Shall we look at another one of these questions? if January the 1st is a Friday and it's a leap year, what day would January the 1st be on next year? So hopefully by this stage, we're not going to start adding sevens until we get to a big number. Hopefully we can find a bit of a shortcut. So we'll give you a couple of seconds to have a think about that question. So that's this one. So if January the 1st is a Friday and it's a leap year, what day would January the 1st be on next year? And actually, in some ways, this might be an easier question because there isn't the temptation to think about adding on 31 to 31 to 1.
A few people have been suggesting the day. It'd be quite nice to know how you've been getting, whether Claire has assumed you're not adding lots of sevens. How are you coming to that decision?
Yeah, there's some nice,
Yes.
nice explanations coming in. So I think this.
Yeah, I'm not quite sure how everyone knows that it's 52 remainder 2. I know that when I looked at the problem, I thought to myself, oh, I know that 35 is in the 7 times table, so I know that 350 is in the 7 times table, so I can ignore 350 and see what's left. I've got another 16 to go, so that's 14 plus 2. I can ignore the 14 because that's just like the hands of the clock going round twice. And then I've just got to add 2 more days. And like everybody else, I came to the Sunday. Good. Okay. So that was the first problem in the feature, clock arithmetic. And then, Claire, you're going to talk about more adventures.
More adventures, yeah. Yeah, so more adventures. Well, there's 2 problems that can sort of follow straight on from clock arithmetic: clock squares and more adventures. The one we wanted to look at was more adventures. And we're now stopped calling it clock. We've now gone to modular arithmetic, but it's the same thing. And this question asks you to start by thinking about 2 numbers, so 20 mod 7 and 60 mod 7, and what happens when you add them together. So I can see that 20 mod 7 is equal to 6. 60 mod 7 is equal to I've now forgotten what it's equal to. 4, isn't it?
Yes.
Yeah.
56
Yeah.
is 0.
And then 80 mod 7 is the same as 3. And then you also notice that if you add up 6 plus 4 mod 7, you also get 3. So what we've suggesting people do is start by trying a couple of different numbers, see if you notice a pattern. And then we're asking if in general, if big A is equivalent to little a mod 7 and big B is equivalent to little b mod 7, is it always true if you add them up, you get something that's equivalent to little a plus little b mod 7? And we've developed a proof sorter for this. And for some reason, you sometimes have to refresh the page before it shows. We need to ask Oscar about that. Okay, there it is. So you might have to refresh the page a couple of times. The way these proof sorters work is that you can shift the statements around and get them into what you think is the right order. Once you've started moving them about, it will give you a submit button to press. So if I just shift a couple more about.
Claire?
Yeah.
I tend to move my cards and put them below rather than, so.
Oh yes, there's lots of space down there.
There's, yes, and then you don't get
Yeah.
that submit button coming and pestering you. And it means it's easier to make spaces at the top. And if you want to, well, I mean, the top and the first one and the last one are possibly easy ones to fill in.
Yeah.
Okay.
So can anyone suggest what might be a good first statement to have in our proof? You can just give us the first little bit of the statement. You don't have to try and type out the whole thing. And quite often with these proof sorters, there are some hints as to what might be an initial one.
Okay, so Ewan and Nikki are suggesting if big A is equivalent to little a mod n.
Yeah. Okay, so we'll put that one first and then suggesting this one. Okay, before we do the middle bit, what is probably a good last statement? And there's a hint in the wording again. Yeah, we're trying to model correct use of mathematical language as well when we're creating these proof sorters. Okay, so we have some people who think therefore, so I'm going to try and move the rest of these out the way. Okay, I think if we just say first, second, third, fourth now, rather than trying to write them out of first. Charlie, can you see my mouse when I'm wobbling like this? Yeah. When we, out of first, second, third, and fourth, which do we think we'd want to put next? Okay, so we've got a couple of people who think we'd quite like to put this one next. Okay. Oh, we had disagreement. Somebody thinks fourth. So somebody thinks that one next.
Yes, but it's no longer called the fourth one.
It's no longer called fourth one because I've just moved them. So I think what we're trying to do here is we're trying to show every single step with no algebraic simplification going on. So I think the next one is actually this one, where we are just adding A and B together without rearranging anything. And then this one rearranges them so that the n terms are at the end. Right, we have two more statements at the end. Let's call this first and second. Which statement do you think we'd like to put in next? Okay, we've got a couple of people who've gone for second. So that one goes there. And then if we try it, yeah. So the first two statements could actually go either way around, but it's only this way that it actually says it's correct. But if people aren't putting their A and B in alphabetical order, then they lose style points anyway. Underneath the proof sorter, we've asked them to start considering two numbers multiplied together. And we've challenged them to actually try and create their own proof. So we won't go through this now, but that's something you to go away and have a play with yourself. It's more challenging than using the proof sorter, but it's sort of the next step. And what we've also done is we've got an example proof for them to click on so they can compare what we've written to what they've written.
Yes, I'm imagining some
yeah.
students might look at the proof sorter and use that as the model for how to lay their proof out for the multiplication. And like you said earlier, we're trying to introduce setting out a proof in as rigorous a way as possible. So hopefully the second part, where they've got to produce the proof themselves, is slightly more accessible because we've offered them the proof sorter initially.
Okay, the final part of this problem is talking about equations using modular arithmetic. We get some interesting things happening. So I'm going to start by asking you if I know that 4 times x is equivalent to 2 mod 10, and we'll say that x has to be in the range 0 to 10. Can you solve that equation and tell me what x must be? So one technique is just to start with x equals 0, x equals 1, x equals 2, multiply by 4, and then try and find a solution. And thank you for putting in x equals, because that makes it easier to distinguish it from the last question we asked. And if you found one solution, can you find a second solution?
You're forgiven. So shall we check that the two solutions that have been offered?
Yeah. So if x equals 3, we have 4x is equal to 12. And if we consider that mod 10, I'm going to start thinking about remainders now because it's.
You've written mod 2, Claire.
Oh yeah, I've written mod 2, mod 10. It's a bit like my differentiation last night. So 4x equals 12. So if you think mod 10, 12 is equivalent to 2 mod 10. If instead we have x equals 8, 4 times 8 is equal to 32, which is also equivalent to 2 mod 10. So mod 10 is quite a nice number to work in because it's very, very easy to see what the remainder is when you divide by 10. Okay, let's find another equation.
How about 6x equals 4?
Okay, 6x equals 4.
And let's carry on working in mod 10.
Yeah. Okay, so have a think about that one, and in the chat, suggest what x might be.
And again, I think there are two solutions, aren't there, Claire?
I think so. Okay, so we've got some solutions coming in.
can I just check, Claire? One way that you would go about this is to say, okay, let's think about the 6 times table. 6 times 1 is 6, 6 times 2 is 12, 6 times 3 is 18, 6 times 4 is 24. 24, that's the same as 4 mod 10.
Yep.
And then I don't expect you to write the whole of the 6 times table, but dot, dot, dot. Oh, maybe you will. 54.
Doesn't take that long.
And that's,
yeah.
So when x is 4, 6 4s are 24. When x is 9, 6 9s are 54. And both of those are the same as 4 mod 10.
Okay, let's go for another equation. 6x, and I've just got rid of all the 6 times table. 6x is equivalent to 7 mod 10.
We're going to get good at our mod 10s.
Oh, I like the alternative way of doing it. Yeah, like a lot of these things, there's more than one way of arguing it. So thinking now about 6x is equivalent to 7 mod 10. And we've had one suggestion that there isn't a solution. Can you explain why there isn't a solution? Yeah, there's some nice explanations. Multiples of 6 have to be even. I don't think that's a complete argument, as we'll see with our next question. Multiple 6 do have to be even, but that's not quite enough to prove it. Oh, right, sorry, it goes with the previous answer. Okay. Shall I do a last equation, Charlie? Or one more?
Okay.
How about, so, 6x has to be even, we know that. How about 6x is equivalent to 7 mod 11? Does that have any solutions? So again, you could start working through the 6 times table. What value of x gives 6x equals 40?
I think there's just going to be one solution in this case, Claire.
Yep, I think there's going to be just one solution, which is the x equals 3 case. So it's not the problem wasn't that 6 times x was even. There was something involving the modulus as well, and there's some connection going on there.
Can we do another one that's impossible?
Yep. So if I have,
what about 5x equals 3 mod 10?
Mod 10. So we'll tell you that is impossible. Can you explain why it's impossible? So you can just put something in the chat to say why you think this isn't possible.
And you're not allowed to say it because Charlie and Claire say so.
We have been known to be wrong from time to time. Yes, I like that explanation.
Yes, 13, 23, 33, 43 are all equal to 3 mod 10. Whereas multiples of 5 will end up in either 0 or 5.
I also like using the algebra to, I always like a bit of algebra, but using the algebra to try and solve this. So if something is 3 mod 10, you know it's got the form 10 times something plus 3. So x is going to be equal to 10n plus 3 over 5, which is 2n plus 3/5. So it can't possibly be an integer. So this bit's an integer, adding on 3/5 is not an integer. So there's no solutions, which is a really nice way of thinking about it. At the bottom of this activity, we've put in something called stars. And stars is also a problem in its own right. But you can use this to try and illustrate what's going on. So if I think about the 6x equals 4 mod 10, I'm just going to change this so we've got 10 points. The thing that slightly irritates me is that we haven't got a circle at the top here. So when I'm doing that, I tend to make this one my 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. But you can obviously start numbering wherever you like. If you don't mind being sort of slightly on a tilt, you can start your 0 up here. If we were looking at 6x equals 4, then what we can do is we can demonstrate jumps of 6. So if we start at 0 and then jump to 6, and then what it's going to do, it's going to keep jumping around 6. So the next one it's going to go to is going to be 12, which will be the same as 2, because 2 lots of 6 is 12. And then you can see that it has hit 4. So we know there's a solution to 6x is equivalent to 4, but it hasn't hit 7. So there's not a solution to 6x equals 7. However, if I change it to 11 points, now my numbers are all in the wrong place, but it does hit every single point. Shall I demonstrate this with one more, Charlie? Let's do 5x equals 3. I've lost my drawing.
Oh yes, 5x is a nice one to do.
Yeah.
Sorry. Yes,
mod 10.
In mod 10.
Yeah. So if I go back to 10 points.
So the number of points represents the mod, and the number of gaps between where you start and where you take your first step is the multiple of x that we're talking about here.
So mod 10, so I'm going to go 5 gaps, 1, 2, 3, 4, 5, and then you'll find it just sort of pings back and forth. And that's like your numbers are either 5 or 0. Okay. And then there's a question at the end which is asking about equations which look like ax is equivalent to b mod n, and when can you have solutions and when don't you have solutions. So this idea that you've now got equations which sometimes have no solutions, sometimes have more than one solution, sometimes have one solution is quite a nice counterintuitive idea, which comes with modular arithmetic. Right, I'm going to, how are we doing for time? 15 minutes. We'll very quickly show you one more problem from the secondary feature, which is clock squares. And then we'll race through the extra parts of this post-16 feature. Okay, clock squares is actually a revamped old problem. You can tell that because of the URL 697. That's quite a small number in NRICH terms, which means that this was originally one of the first NRICH problems. However, we have made it look a bit fresher, and we've added in some extra bits. So Charlie, do you want to start off on this one?
Okay, so let's skip the beginning and just look at the modulo 7 bit there. We've got 1 squared equals 1, 2 squared equals 4, 3 squared equals 9, which is equivalent to 2 mod 7, 4 squared equals 16, which is 2 mod 7. I wonder, could you in the chat post what you think 5 squared, 6 squared, and 7 squared are mod 7? Maybe 8 squared as well, Claire.
Yeah.
So Ewer has suggested 4101. So 5 squared is 25, which is 21 plus 4. So it's 4 mod 7. 6 squared is 36, which is 35 plus 1. So it's 1 mod 7. 7 squared is 49, and 49 is 7 lots of 7. So back to the start. And then 8 squared is 64, which is 1 more than 63. So it's 1 mod 7. And the idea is for students to maybe try this for other module. So work in modulo. There's an example at the beginning, which is modulo 5, I think, and then modulo 11, 13, 17, and to start noticing some patterns. And when the numbers get bigger, they can use the power modulo calculator below. Do you want to demonstrate that now or later, Claire?
Yeah, let's do it now. Let's assume that we wanted to work out 12 squared modulo 10, because that's one that I can check quite easily. So I know that 12 squared is 144. So hopefully we're going to get the answer of 4. So to use it, you put the 12 in here. We're only looking at squares, but this can be used for higher powers as well. To modulo, what did I say, 10, and then calculate, and we get the answer 4. So it will help take away some of the churn for the students. And there's some really nice patterns to notice here and to try and explain. So we've got the numbers 1, 4, 2, 2, 4, 1, and then 0. So we've got 1, 4, 2, 2, 4, 1. We're going up and down in a sequence. Go on, Charlie.
Well, I think what's nice about this is we can explain it. In a lot of what we've been doing so far this afternoon, we've been expecting everybody to reason and explain. And so perhaps modular arithmetic is not in the syllabus, but there's been a lot of playing around with numbers, thinking about multiples, and thinking about how numbers might work. And it's a way of consolidating our understanding. But what's quite nice here is, of course, once we get to 7 squared, then the whole thing is going to start again. When we get to 14 squared, it's going to be 0. When we get to 21, so this pattern we expect to carry on again and again. But also, not only do the patterns repeat themselves every 7, but within the pattern, what Claire was alluding to, the 1, 4, 2, 2, 4, 1, is that within each pattern, there is a symmetry. So why should 1 squared be the same as 6 squared? Now, if we think about what we did at the beginning with clock arithmetic, 6 is like -1. It's like, instead of going clockwise 6 places, you can get to the 6 by going 1 place, 1 step anti-clockwise. And so squaring 6 is the same as squaring -1. And squaring -1 is 1, which is the same as squaring 1. So perhaps that's not such a surprise. And likewise for 2 squared is going to be the same as -2 squared. So that's why 2 squared.
5 squared is going to be the same as -2 squared.
Yes.
Yeah.
And so we get the same answer for 2 squared and for 5 squared. And whenever we work in a negative, in an odd modulo, where students might start noticing that, and all of a sudden be able to work out things like 101 squared in mod 7, predict what it is, and then use the power modulo calculator. So if I'm trying to do, can I predict 101 squared? So I know 70 squared is going to be 0. If I add another 28, I get to 98 squared. So 98 is a multiple of 7. So 98 squared is 0. So 101, can we check on the calculator? I think 101 squared modulo 7 is going to be the same as 3 squared, which is 2. So let's see.
Modulo 7, which is 2.
Aha. So this activity, this task is said, getting children to think about patterns, to notice both the cyclical nature, but also the symmetry within each, and then to be able to use this, to be able to generalize, to be able to predict, and then have the power module calculator to check. So it's not on the school curriculum, but there's a lot of reasoning here, a lot of looking at patterns and making conjecturing and generalizing, which is at the heart of a lot of rich mathematical tasks. We could carry on, but I think we need to move on to the cryptography. Otherwise, you won't see how all this ends up.
Okay, so navigating to the post-16 feature, we've got clock arithmetic, more adventures with modular arithmetic, clock squares, something called Euler's totient function. Euler's totient function is used within the public key cryptography article. So we've written a little problem where students can explore it, and it's all to do with coprimes. So just to explain, I won't go into this, but Euler's totient function is the number of numbers which are co-prime to what's in here. So if you think about 6, the co-prime numbers are 1, because the highest common factor between 1 and 6 is 1, not 2, because they've got a factor of 2 in common, not 3, because they've got a factor of 3 in common, not 4, because they've got a factor of 2 in common, 5, and then not 6, because 6 and 6 have a common factor of 6. So phi of 6 is equal to 2, because there's 2 numbers which are co-prime. So there's a little problem about that. We have the article on public key cryptography. Now it's quite long because we've put in lots of examples throughout. In the setup, it talks a little bit about Bob, Alice and Eve. Now, Bob, Alice and Eve are the usual characters in cryptography problems. So Bob and Alice want to exchange some information, but Eve is listening in and can hear what they're saying to each other publicly. So like a telephone tap or hacking their emails.
I think you should mention that Eve is called Eve because she's eavesdropping.
Eavesdropping, yes. So most of the time, Bob wants to get some information from Alice. So he is asking Alice for information, Alice sends it, and they're trying to do it so that Eve cannot tell what's going on. And the idea behind public key cryptography is that Bob can send Alice a key so that she can encrypt her data. Eve will see the key. Eve will also see the encrypted data, but you can't use the same key to decrypt it. It's what's called an asymmetric system. Bob can decrypt it using a decryption key, which is something slightly different. And this is how you transfer information on the internet safely. You use one of these asymmetric algorithms. So there's a bit of the history. There's here's the totient function cropping up, and then there's some examples. But the exciting thing is the interactivity that we've developed so that you can actually try this out for yourself. There are a couple of ways that you can play it. You can do it in a classroom situation where you set 3 people to be Alice, Bob, and Eve, and Alice and Bob try and send a message between them, and Eve sees what they're saying to each other and tries to crack it. You can also play it in a 1-player mode. So if we assume that we want to play, we'll go with Alice. There's not actually a lot to do with Alice. Alice simulated means the computer is going to play the role of Bob. Then Bob sends Alice a couple of text messages. He tells her what numbers he wants Alice to use. So he wants her to use N is 2923. N and E are all explained in the article. That's some bedtime reading for you. And then what you can do is you can type in a message like, hello, oops. The message gets coded using some small numbers, and then you can encrypt it. And you can send it. And then Bob says, yes, he's got it. If you want to play as Bob, there is a little more to do. You have to actually work out the values. So you have to pick some primes. This is all explained in the article. And then you can send a code to Alice. Alice will send you something back, and then you can decrypt it. I don't know if we've time to very quickly do this. I know some numbers at work. 7 and 11. N is 77. 5N is 60. Did 13 work? Yes. Ah, there you go. I could remember some numbers at work. Okay, Alice gives us a message, which we can type in here. 69, 42,
65, 17, 29, 4, and 54. And has sent us the word cupcake. And then the final one, which is the one that we had a lot of fun with, is playing Eve. So the primes are not that big, which means that you can actually crack these codes. So if you play as Eve, you can see everything that Bob and Alice are saying to each other. So you have to try and crack the code and work out what the secret message is. And in getting started, Charlie and I have done a couple of videos showing us being Bob or being Eve in the simulated mode. So if you've got some sixth formers who want to do something a little bit different, perhaps they might be doing what's called an EPQ,
extended project qualification, they might want to look into public key cryptography. This is something that you can point them at. If you've got some keen Key Stage 4 students, they might like to have a play with this and see if they can decrypt the messages. Well, we've got 1 minute to go. All good stuff for IB students as well. Yes, I mustn't forget the IB students. Right, Charlie, is there anything else you'd like to say at this point? Or
no,
in 30 seconds.
Yeah, go back maybe to the homepage and just remind everybody how to find the feature.
Yeah, so to find the post 16 feature, if you click on post 16 and then go to latest feature, that will take you straight to the latest feature. We don't have a separate student and teacher page for post 16.
And if you click on it, Claire, I think at the top, it shows that a lot of the problems are live problems, and there's a deadline for sending in solutions to our live problems, which is in about 4 weeks' time. It's usually a couple of weeks before the next holiday, so before the half term. So there's material, there are resources there, challenges there for Key Stage 3 students, for Key Stage 4 students, and what we've just shown for Key Stage 5 students. I think that might be all.
Yep.
I don't know, Liz, Ems, is there anything else that you think we should be asking about?
I don't think so. Thank you very much, Claire and Charlie. I think what's left for me to do now is just to go through a few little reminders before we say goodbye. Claire, I wonder whether you could stop sharing.
Oh, of course I can.
Please,
yes.
that'd be wonderful. And I'll just put up another PowerPoint. So we would like to remind you that if you don't already follow us on Twitter, please do. That's a great way of finding out about future events, and you may like to chat online about today's session this afternoon using that hashtag. If you prefer, or in addition, you might like to sign up for our email newsletter, which we send roughly once every half term. What Claire and Charlie haven't mentioned, but we'd really like to be aware of, is the fact that we do have a secondary curriculum mapping document where we've taken all the mathematics objectives from the Key Stage 3 and 4 national curriculum here in England, and we've linked them to NRICH tasks. You can find a link to that on the secondary teacher homepage. So if it's not something you're already familiar with, do check that out. As I mentioned right at the beginning, we will put up a recording of this webinar on the NRICH site at that page, and you will get an email reminder of that. So please feel free to share that with your colleagues. Finally, I also mentioned at the beginning that we're very grateful to Trinity College for funding today's event. We do hope to run similar future events, and therefore we would love your feedback. We want to make them as useful as possible to you. So please follow that link and tell us what you thought of this afternoon's session. I think, therefore, we've come to the end of working together. Thank you very much for participating on the chat. Incidentally, if you wanted to save a copy of the chat, do click on the 3 dots that you'll see in the chat window, and you'll get that option. So I think, unless there's anything I've missed, Claire, Charlie, Ems, I think it's time for us to say goodbye and thank you very much, and hopefully see you again in the future.